I'm John Linford. I'm with ARM in Austin, Texas. So ARM makes a profiling toolkit called Forge, and it includes a debugger and a profiler, and those are available on Magnus, and so they might also be available on Galaxy. But yeah, Posi licenses the software from ARM, so it's available on the systems. So you can still run very complicated and important jobs on the system, but then get this information back that can guide the optimization and inform the scientists about where things could be improved. We came to the GPU hackathon first to support Posi. Posi is a really important supercomputing site for ARM, and bringing the domain experts, the systems experts, the computer scientists, and the physicists all together so they all can collaborate and get their heads together and really work out the problem. That's where the value comes from. So that is the ultimate goal here.
Okay, so we were unknown beamforming pleasures, and we are interested in studying pulsars. So where our code its purpose is to take the signal from the MWA and to turn it into a pulsar signal that we can study. You'll notice that the telescope that we're using here doesn't have any moving parts. So in order to maximize the sensitivity in a particular direction on the sky, we need to manipulate the data coming into each of these tiles electronically, and that's the computationally expensive part that we wanted to optimize for. So when we arrived here at the beginning of the week, this is what our code looked like. So there was a bunch of time spent reading the data, a bunch of time spent writing the output, and in the middle there's a bunch of time spent obviously doing the calculation. The bulk of that calculation had already been implemented on GPUs, but in the most naive way possible, because that was me doing it for the first time. So when we arrived, our thought was that what we wanted to do, because actually you have to choose which direction in the sky you want to look at first, it would be really good if you don't know where the pulsars are to be able to point to choose multiple directions and do that whole process simultaneously, making the whole pipeline parallel for different pointings. But as it turned out, we have these other 4 different kinds of optimization that we could have done, and which we have been working on throughout the week. So the first kind was looking at the amount of time spent in the existing GPU kernels and optimizing those. So I showed you 2 little sections, 2 parts of that calculation, and I managed to get the first part optimized quite well with a if you're just looking at just how much that sliver was reduced in size, then that's a factor of 4, which in terms of the whole program turns out to be about a factor of 1.5 speed up. But I didn't get time to do the other kernel, so that can now be done from what we've learned this week later, and hopefully we can get up to a factor of 8 speed up just in that aspect. The second kind of optimization was noticing that actually some of these, the reading and the calculation and the writing can be done in parallel in a sense. So we can be reading in data while another stream is doing the processing, while another stream is doing the writing. So that kind of optimization we would expect possibly a speed up factor of 2, but from our discussions we've learned that we might even be able to get better than that, so 2.5. But we haven't actually finished implementing that bit yet, so I can't report any actual speed up factor for that one. So a third part of the optimization is looking at all the other bits of code that I haven't mentioned, which is still in CPU land, but didn't have to be. Hopefully we can cut that out like that, or absorb it into a GPU kernel, or create a new GPU kernel to do it. So Paul has been working on that, and at the beginning, we expected possibly to get it down by a factor of 10. As it became apparent what it was doing, we now expect that once we're finished with it, we'll get a factor of 4 speed up for just that bit, and at the moment we're up to a factor of 2. So, but again, remember that that's only a small percentage of the total execution time, so that 1.1 in brackets represents a 1.1 speed up, even if that factor of 10 was completely realized. The fourth kind of optimization is not really optimization for speed up, but just more efficient use of our resources. Because currently what we had our data, incoming data split up into 24 frequency bands, and each band was being assigned a different job on Galaxy, and on Galaxy there was only one CPU and one GPU available per node. So on other architectures like Athena or other ones that we might be using in the future, there might be more GPUs available per node, and at the moment our code is not written in such a way to take advantage of that. So Brad has been working on that to make sure that we're distributing our jobs in the most efficient way possible. That doesn't equate to any actual speed up of the code. It's just about making better use of our resources. And finally, there's this multiple pointings part of the aspect of our code. And I guess naively at the beginning you would think, oh, well, if we can do that, we can get an effective speed up. Rather than doing the pointing serially, we can get an effective speed up by a factor of however many pointings you have. But as it is, Nick has been working on that, and just this morning he managed to get something working. So we've tested it on 7 parallel pointings, and he saw a 7 times speed up, which is fantastic. Apart from continuing to work on each of these optimization aspects and getting them all streamlined, there is the matter, of course, integrating them all together, because they do interact, and it's not going to be trivial to just make sure that we get all of these optimizations in at the same, easily working together. So it may be in the end that after all that F there is still not 1, but something close to 1 we hope. So that's what we have achieved this week, and we have an excellent idea what we're doing moving forward. And there we go. Thank you very much.